All right, so we're looking at conservation of energy. Specifically, what we're looking at is conservation of mechanical energy. Mechanical energy is just potential and kinetic energies. So we're going to see these guys change back and forth between each other. Um, if we had a situation where we would have non-mechanical energies, that would be anything besides potential or kinetic energy. So thermal energy would be an example of a non-mechanical energy that would be classified here. So conservation of energy states, like all the conservation laws, that energy can't be created or destroyed. So basically, when we look at a problem, whatever energy we have at the beginning, we have to end up with the exact same amount at the end. And that doesn't mean it can't change forms. And that's actually what we're going to look at in these problems is that energy changing one form to another. Sometimes it's complicated, sometimes it's more straightforward. Ultimately, that's what we kind of have to think of is every point during the problem the energy has to be accounted for. So we've got this example here, which is a non-friction example, where we've got this sled or something sliding down a hill up at the top, given a gravitational potential energy value of 100 joules. And as this thing slides down the hill, that potential energy becomes kinetic and it speeds up until right at the bottom of the hill, all of the gravitational potential energy is gone because it's no longer above the ground and it's now moving at its maximum speed. So all of that gravitational potential energy became kinetic energy. And so you see we accounted for at the end of the problem every single joule that we had up here at the top. There's a situation there in the middle. Right in the middle, we have still 100 joules, but it's now evenly split between gravitational and kinetic energies. So that's kind of the general idea that we're looking at with these problems. That's the no friction example. If we look at something down here where we have friction, the idea stays the same. Whatever energy you have to account for at the end of the problem. You notice in this one, you start off with 100 joules, and then only 90 joules shows up down here at the end in terms of kinetic energy, which means this guy's going a little bit slower than our example up here. But we have to kind of backtrack and say, where did that 10 joules of energy go? And the answer to that is it got turned into non-mechanical energy. I'll kind of draw this in red there in terms of friction on that track. And so there's still 100 joules left, even though there's only 90 that shows up. The other 10 is this friction right here. So here's your 10 joules of thermal energy that got transferred added to your 90, and you've tracked down all of the starting energy. So regardless of if it's friction or no friction, you can still account for all of the energy. The friction examples, it just makes it a little more challenging to find it all. So that's the general setup that we're looking at here. We're going to look through a little bit of the math now for some of these examples. So let's draw just that basic example of something going down a hill, starting off with PE up here, and then ending up with down here. Mathematically speaking, the way we're going to set this up is what I would suggest is a starting equation that looks like this. So I'm going to write this out. And I would write this at the top of each problem that you do, and this will help you get things started. Basically, this is the start of the problem, and then the end of the problem is over here. At the start of the problem, ask yourself, is the object above the ground? Is the object moving? So in this case, let's say that this sled's up at the top of the hill. It certainly has potential energy up there. It is not moving, so there's no kinetic energy in the beginning. Over here at the end of the problem, this object, this sled, is no longer above the ground, which means there's no potential energy, but it is moving. And in fact, it's moving as fast as it's going anywhere on this diagram. So we get a situation where we have PE in the beginning and we have KE. And we've looked at both of these individually, so we've seen the equations that we need, and now is actually the time that we'll plug those equations in. So our gravitational potential energy over here is mgh, and our kinetic energy equation is 1/2 mv squared. And so at this point, you see that both sides are multiplied by mass, and so those are going to cancel out. And so we're left with an equation that looks like this. And let's say we're trying to solve for this velocity, so how fast this thing's going at the bottom of the hill. All we have to do now is rearrange this, get v by itself. So I'm going to multiply both sides by 2. And then I'm going to take the square root of both sides. so that I get a velocity down there at the bottom of the hill of square root of 2gh. From there, basically all we would have needed to know is the height of that hill, and we'd be able to solve the velocity of this thing at the bottom. So that's kind of the way some will set up. If we had a more complicated scenario, so maybe let's repeat this hill over here. And instead of letting it go all the way to the bottom, let's park this thing somewhere here in the middle. And so at the beginning, we have PE. At the end of this problem, this thing is still above the ground. So this is a situation where here we have PE and KE. So this is going to be a more complex math problem to set up. I would still set this up like we did the other problem. Like this. There's no KE in the beginning because this thing is not moving. But at the end, there is both PE and KE. So these two both have to stay here. They aren't going to cancel out. And so we can rewrite this and expand it out like this. And I added little subscript letters here just to help us kind of differentiate between this height that's the initial height and then the final height that's over on the right-hand side of the equation. You notice that each of these places all get multiplied by m, and so our masses still cancel out since everything gets multiplied by that same number. And then we can solve for any of the possible variables on this one. Let's say we wanted to solve for how high this thing started, so this initial height. So let me kind of rewrite this and kind of simplify it down first. So we end up with that. And we're trying to isolate this guy, which means all we have to do is divide both sides by g. And we get it set up like this. And this would assume that the problem gave us a couple numbers, the final height, the velocity, and we could plug in and solve this out. So that's kind of the approach to use. Write out this base start equation, look to eliminate stuff, and then expand out, and then kind of simplify down to whatever it is you need to plug in.